Come up with some interesting ideas which generalize our understanding of static electric charge. So, let's start by kind of lay out some basic definitions and sort of piece it together in terms of what it means in electrostatics, or for that matter, even electromagnetism in general. To begin with, we have this idea of flux. And fundamentally, let's sort of establish what the idea of flux means. Canonically, what does flux mean, right? From Oxford Dictionary or Webster or whatever. Any idea what flux means? Aside from how you flux metals in a solder board? It's a flow.
Yeah.
It's just a flow. Okay. So the idea of flux, fundamentally, this isn't something we dealt with. In fact, there's a corresponding flux associated with fluid flow that we just didn't deal with when we were talking fluids last quarter. But the idea of flux is that you have something flowing into or out of something. In our case, the idea of using flux is going to establish how something flows through a defined surface. So we may just sort of establish, well, what might be an example of flux. One example of flux might literally be light. Radiant energy, if you will. That transmits through a window. Just basically, you've got a window and it's a light that passes through. Another example might be if you got your windows open, on a rainy day, you're driving down the road, be the flow or the rate of water that flows, or raindrops that physically flow into the cabinet or the compartment of your automobile. So that's essentially the idea. Now, as we apply it to, in a physical sense, we typically think of it as the rate of flow, most often associated with this idea of field. Not necessarily just electric field, but our concern is field flux. Through a defined surface. Now, the example might be, say we have an electric field. And we don't worry about what generates this electric field, but we have some electric field, and this electric field is uniform and horizontal. So, if we were to make a coordinate system, something that looks like this, then we could write this electric field in this region as being related to whatever the magnitude of the electric field is in the I direction, and no electric field in the J direction. And maybe we establish that the magnitude of the electric field, E if you will, is, I don't know, about 100 newtons per coulomb. So basically we have 100 newton per coulomb electric field, and it's just horizontal. Now, if I were to place or if I were even just say to define a rectangular or a rectangular surface that is flush or oriented, maybe not flush, oriented normal to this electric field. So we'll just put a flat rectangular surface. And I'm just going to define this surface. It's just in space. And the face of this surface is normal to the field. So if you want to think about it, the face itself, if you were to move along the face, you would move purely in the in the YZ direction without ever moving along X. Okay, it's just to keep it simple. Then the way we would calculate the electric flux would be to say, I've got a certain amount of electric field. And that amount of electric field is a constant value, and it's uniform through this surface area. So if I took the magnitude of the electric field and multiplied it by the area of this surface, and let's give the area some value. What? 20 by 20, so maybe 0.04 meters squared. We just calculate the flux by measuring the flow of this field through this surface area, or times A. And that's how we would calculate the flux. So in this particular case, it would be 100 newtons per coulomb. And we would multiply this by 0.04 meters squared. So what's that, 4 newtons per coulomb, meters squared, or meters squared per coulomb. So I've got this uniform flow of field. Whatever its magnitude, because it's even throughout, if I multiply that by the area, that defines the flux that's passing through or flowing through this material or this surface. And this is just how you calculate it, at least in the simplest case. We'll define it more and more rigorously as we move along. Now, just a couple little things about this, and it's at least worth noting. Based on this definition, and this would be true generally speaking in fluid mechanics or otherwise, I'm writing this backwards, I don't know write this. You might think about this. If I divided both sides by this surface area, I've got this electric field that's flowing. You may just note that as we define this electric field, really what it represents is the area density of flux. So if flux is the something that's flowing, the electric field is the density of that flow. So in some ways, flux is probably, it's a sort of backwards history because we didn't start with this idea of flux. But in some ways, flux is more fundamental than electric field. If you think about it this way, for a given surface area, it's kind of like counting electric field lines, where the electric field lines and how they're spaced is scaled to the magnitude of the electric field. Okay, so that's what it is, and we'll get to the why and all of the concerns with it. But if we were to take the same electric field and just consider a situation where maybe we rotate the same surface, some angle. So here's same field. Rotate at some angle theta. And I'm just going to rotate it over. So now I'm going to take the same size of this thing and I'm going to rotate it some angle. If this was the horizontal, I don't care which one, I'm just going to call this angle theta. I just rotate it. It's here, and I guess I better define it this way. I'm rotating it theta, like this. Okay. Well, if you step back and look at that, just on the surface, or the pun, with respect to this surface, there are fewer field lines passing through. Why? Well, simplest answer is the effective cross-sectional area is smaller relative to the moving field that's passing straight. The way we would calculate the field in this particular case, or I'm sorry, the electric flux, we know that we have a constant field, so I'll just write it as x. We know that it is a same constant surface area. I really shouldn't have chosen that surface, but since I did, the effective surface area. No, that's a cosine.
Yeah.
It's basically going to be something smaller. When the angle is 0, then you've got maximum electric flux. You've got maximum field lines passing through. As the angle tips, you get fewer and fewer of these field lines, so you have less flow through this surface, if you will. And if you wanted to think about it, this is the effective surface area with respect to that, to the flow of the field. So in this particular case, I don't know, what, 30 degrees? Something like that, just throw a number in here. So now we have basically 4 Newton meters squared per coulomb. That was the original value. This part doesn't change. Times the cosine of 30 degrees, so it'll be slightly less. And 0.866, 0.866 times 4, so it's going to be 3 point something.
3.46.
3.46. I was going to say 0.46, I'm way off. Okay, so 0.46 Newton meters squared per coulomb. Okay, so that would be how you would calculate the flow in this case. And you can sort of see that if you rotated it completely flat, then because all of the flow would basically skim the or all of the field would skim the surface, you would essentially have no portion of the electric field passing through the surface. So this is sort of the idea of a flux. Now in this case, this flux is an electric field flux. But the idea is essentially this. If you have some surface and you have some field passing through the surface, if you can evaluate the quantity or a field that passes through that surface, over that surface, then that's how you would define the flux. Now, in general, for any given surface, because of this cosine relationship, let's just note that in this particular case, this angle corresponds if I were to draw a line this direction. This is the direction of the face itself, of the open face. This angle theta corresponds to this angle theta. This angle is the angle between the electric field itself and the direction of the face. Also, we can define the surface area with its orientation relative to this face as an area vector. This is for convenience and it's necessary, and it's not really a vector in a sense, but it's an area that's pointing with a certain normal direction to the plane of the area. And that area we could define as whatever the area of the surface itself is, pointing in the direction, I'm going to call it normal, the direction normal to that face. So this would be the IN direction, if you will. So we have basically a surface vector we can define this way. What we're left with then is an area vector and an electric field vector. And they're related by this angle. When they line up, you have maximum flux. When they're normal to each other, then they're zero. This electric field flux, or flow, through any given surface then can be defined as the electric field that passes through the surface times scalar product, this area field vector. Or I'm sorry, this area vector. And because it's a scalar, basically what this means is it's E, for this particular case, for a uniform field, E times A times the cosine of the angle between the E vector and the A vector. The key is knowing that orientation. So this is the idea of flux, and unto itself, it is what it is, I guess. The question is, how is it useful? And we'll start by asking just a fundamental question. What is the source of electric field? Always, what's the source of an electric field? Electric charge. So whenever you have an electric charge, you have a source of electric field, or if you will, a source of electric flux. Or again, the field is just the density per square meter of the electric field itself. Or I'm sorry, of the flux itself. Sending it backwards. So field lines, area density of the flux. So it turns out, and this is where it's kind of cool. Erase this for now. It turns out for any given amount of electric charge, for any given charge, I'll say quantity of charge, it's only got so much electric field, it's only got so much electric flux. Well, the field will vary if it's a point charge radially from the center. But it turns out that for any given amount of charge, there's only so much of this flow out of it. That kind of makes sense, right? If charge produces this flux flow, a given amount of charge is only going to have so much flux. And if we multiply the quantity of flux by the permittivity constant, that quantity is equal to the electric charge. Always. Because any given charge only has so much flux, and they're related by this physical constant. This is, at one level, why epsilon naught is a little more useful physical constant than the Coulomb constant K. Because it's more fundamental to the relationship of electric flow substance and the charge that produces it. So this is called Gauss's law, and this is fundamental in nature. So on the surface, it says something very fundamental about the relationship between electric charge and what flows out of that charge as it disturbs the space around it. Fundamental in that sense. In fact, it's one of 4 simple relationships, simple maybe not so simple, that define all of electromagnetism. That's all. Now, to this end, let's just note a couple things. Because Q is quantized, so is this idea of flux. The amount of flux you will always have, the total amount of flux, anywhere, if it's associated with any given charge, the maximum amount of flux you can have, or the minimum amount of flux other than 0 associated with an electric charge is going to be when the electric charge is E, 1.6 times 10 to the negative 19. Now, let's just note that 1 E of charge, right, that's 1 quantum of charge, generates, and now generate is probably a bad word, probably more there's associated with it, but it generates a unit quantity of flux that's equal to the magnitude of this E divided by epsilon naught. Or 1.602 times 10 to the negative 19th coulombs divided by 8.86 times 10 to the negative 12 coulombs squared per Newton meter squared. This is like 0.2 times 10 to the negative 7, so 2 times 10 to the negative 8, a little less. 1.7 times 10 to the negative 8, maybe. Units would be Newton meters squared per coulomb. Okay, so all magnitudes or quantities of electric flux are multiples of this number, in the same way that all electric charge is multiples of this number. So it is a uniform discrete quantity in a sense. Okay, now when does it apply? Well, this is the charge associated total. Or I'm sorry, this is the electric flux associated in totality, if you will. In totality is this quantity of charge Q. So how would we apply it? Well, the way we would apply it would be to take the same idea we took over here. And I'm trying as much as possible to take the esoteric out of what is ostensibly a very esoteric idea. So if it seems like I'm trying to oversimplify it, I really am. Because I'm trying. Otherwise, its meaning gets completely lost in something. And, you just end up using it mathematically, and it's hard to really truly get the brain around it in this form. Okay, so If we just extend Gauss's law, this leads to, if you have a certain amount of charge, and I'm just saying the same thing, here's my charge, okay, here's my Q. It's just a point charge, it's always the easiest one to look at. You have a charge Q, you're going to have field lines pointing like this. I'll just use a positive charge just to make life simple. Right? That's what a field would look like for a point charge. Now, so each of this field, each point of this field, wherever I am, whatever the magnitude, that corresponds to a flux density, or a certain amount of flux per square meter at this particular point. If I were to enclose this electric charge in a closed surface, and maybe I'll even draw it this way to make it, and I'm making it intentionally irregular. I'm going to make a closed surface. If I enclose this surface around this charge, I'll basically capture all the flux. So I'm going to capture all the electric field lines around with some area. So ultimately, I'm going to enclose this charge in a complete surface so that I can capture all of the electric field lines. Okay? If I do that, then what do I know about this Q? Whatever it is, I know one thing. It's going to have a certain amount of electric flux that if I multiply it by the permittivity constant, that will be equal to its value. The definition of electric flux. Well, how do we define the electric flux? Now we have a surface that's very irregular. So we've got to think about what this surface means. If the surface is irregular, whatever the total flux is, if I know what Q is, I know what the flux is. If I knew off by chance what the flux is, I could calculate Q. If I don't know what the flux is, and I don't know what Q is, what I can do is I can take this surface, this is my closed surface, I'm going to break it down into small pieces. How small? Well, small enough so that along every particular region, or every little segment, it's small enough so that whatever the field is, it's constant through that segment. So it just has to be small enough that, that the electric field is effectively constant. So I'm going to split the surface into very small segments, or very small pieces. And each surface is going to have a size dA. Well, now sort of see where this is going to go, right? Where the total area would be equal to the integral, or if you will, the sum of all of these surfaces over the entire closed surface itself. So I'm taking all these little pieces and I'm going to add them up over the whole face of the surface. Now the thing about this is that no matter where I am, each of these little surface segments, if I were to draw this out over here, if I were to blow it up, for each segment I would have a certain dA. And that dA would be based on the size of this and the direction normal to the face. The electric field that passes through this region, if the region is small enough, the electric field is effectively constant through that region. So to calculate the total flux. Now the problem is, depending on how far away I am from the center, the electric field will itself vary, both by direction of orientation and also by magnitude with respect to dA. So every segment of flux associated with every little surface area will be related to the scalar product of whatever the surface area is, or I'm sorry, of the electric field at that particular location. The dot product with the segment of that area, dA. And dA will vary by orientation. Even if you kept the little sizes the same, tiny little slivers, it will vary in orientation as you work your way around this thing. Now again, it starts sliding into esoterics here. Well, what this tells me then is that if I want to calculate the total electric flux due to this charge, I would add up